Okay, good morning everyone and welcome to the 2011 Royal Tyrrell Museum Speaker Series. Today the Royal Tyrrell Museum and its cooperating society are proud to present our very own Dr. David Eberth. Dave is a research scientist here at the Royal Tyrrell Museum and a regular of the Speaker Series. Dave obtained his undergraduate degree in zoology from the University of Massachusetts. He then moved to California to pursue his master's degree in paleontology at the University of California, Berkeley, where he studied Permian sphenecodontids, a group of animals that includes a famous sailback Dimetrodon. Subsequently, Dave moved back to Canada to pursue his PhD in geology at the University of Toronto, where he studied the Permian red beds of the American Southwest. Fresh out of his PhD, Dave joined the ranks of the scientists here at the Tyrrell Museum in 1985, and he has been here ever since. Dave's primary research interests include the study of dinosaur paleoenvironments and vertebrate taphonomy. Over the years, he has conducted field research in Canada, Argentina, Germany, China, Mexico, the US, Mongolia, and last summer he went to Ellesmere Island in the Canadian High Arctic. Today, Dave will present the results of a recent study on the age of the dinosaur-bearing rocks in southern Alberta in a talk entitled A Revised Chronostratigraphy for the Oldman, Dinosaur Park, and Bearpaw Formations at Dinosaur Provincial Park. So without further delay, I present you Dr. David Eberth.
Easy for you to say. Yeah. Thank you very much, Francois. I don't usually use a microphone, but apparently this is being filmed. Is that right? So I'm probably out of the frame now, so it'll just be my voice. Thanks for coming out here. I apologize to all of you if you saw the title of this talk in the advertised somewhere. It was probably the most unpleasant looking thing on the planet. This isn't particularly better, but it's shortened at least. I got lots of comments that people couldn't even pronounce the title, so I guess I've entered a new range. I also want to thank Francois for not listing the dates that I was at all those schools. That was another time long ago. Let me see if I can get this thing working. Usual routine. All right. So what we're going to do today is we're basically going to take a little bit of information that I could probably present to you in about 5 minutes. Some new research results, and then we could all go have lunch and life would be good. But I'm going to dress it up. I'm going to put a lot of lipstick on it and give you a few other concepts. As we go along, though, what I'll do is I'll verbally highlight which slides are the actual key slides, the take-home messages. All right? We're going to be talking about Dinosaur Provincial Park today, and as many of you know, the park is in southern Alberta along the Red Deer River. It's about an hour and 45 minutes out from Calgary, about 45-minute drive, hour and 45-minute drive from Drumheller. Beautiful area, Badlands indicated by brown. This is just this brown area on this schematic map along the Red Deer River, and of course, if any of you have been down there, you know how exceptionally beautiful and well developed those Badlands actually are. This is just one of my stock photographs showing the nature of the Badlands there. In this particular case, a lot of sandstones stacked one on top of another and a couple of people walking through those Badlands. Three-dimensional Badland development, lots of bedrock exposure allowing for a lot of the fossil richness and resources in the park to be exposed and to be available to us. These are just two of our classic specimens that you can see out in the galleries today. But they're poster children, so to speak, for the quality of preservation and the quality of the material at Dinosaur Park. Exceptional, exceptional material. Not only do we get dinosaurs, we get a whole host of other animals along with those dinosaurs. And as many of you know, the park is famous not only because it yields great dinosaurs, but also it gives us a snapshot into the ecology and the combinations of different kinds of animals and environments that are preserved there. So in a very simplistic sense, we can generate a pie diagram like this, indicating that we have terrestrial forms, we've got aquatic vertebrates, and we've got marine vertebrates, all preserved at the park, not all together, but in different stratigraphic intervals. We won't go into the ecological zonations. The point of the diagram, though, is to show you that we've got a huge diversity of taxa and forms, which really gives us some cool insights into the ecology of the area, making the park even more famous and important. This is a really old slide that I put together literally back in the late 1980s. And I haven't updated it because I haven't updated it. But the message is still the same. If we compare the Dinosaur Park formation, the rock unit that has a lot of this fossil richness in it at Dinosaur Park, with rock units from elsewhere around the world, and then we look at the combination of the diversity of dinosaur taxa, Dinosaur Park stands out as having among, if not the richest diversity of dinosaurs. And also we can look at some patterns of preservation. The green portion of the bar represents taxa that are known from really good, excellent specimens, like those ones that I showed you before, articulated, well-preserved specimens. And the yellow, topping up the bar, indicates taxa represented by fragmentary material. Dinosaur Park just stands heads and shoulders above many other formations around the world. It's extremely important. And in general, we have historically, for the last 20 years, referred to it as being 75 to 76 million years old. And this is what I want to talk about today, is how we get to these numbers and how we've now improved our understanding of these numbers. These are old numbers. They're no longer in play, but I thought I'd put up this old slide just to reiterate and show you how our understanding of the age of the park has changed through time. So the park's important. It's got some cool fossils, and we've historically considered it to be 75 to 76 million years old. Let's just take a couple of minutes to consider the importance of age assessments, radiometric dating, why it's important, what it allows us to do. Well, when I come at it, I look at it from 2 points of view. I look at it in terms of comparing a location like Dinosaur Park with other places around the world. And by doing that, we can compare evolutionary patterns of animals through time in different places around the world, see how animals are evolving in the same way or in different ways. We can look at for changes in the paleogeography, how the environments are different in places that are the same age. We can look for regional changes in the paleoecology. If we put the paleogeography together with the fauna, we can actually see how the ecology of different places around the world are changing. So by having control, by having radiometric dating control, we actually have a really powerful tool to compare rock units and their faunas and their ecology around the world. We can also look at local patterns, and here at the Tyrrell Museum we tend to focus a lot on these local patterns here in southern Alberta. We are, after all, a provincial facility, and it's important to really understand what was going on here in Alberta. And to the point, we can look at the evolution of individual lineages of dinosaurs. We can look at those evolutionary rates of change. And we can look at, again, on a local basis, we can see how the faunas are evolving and changing, and those rates of change. So just to give you an example of this, if we consider paleogeographic reconstruction of the globe going back into the late Cretaceous, and just ignore these numbers for the time being, what I'm talking about here is the ability to go to different parts of the world, and if we have radiometric control, if we have radiometric dating control, we can actually look at the parts of the rock record in these different places around the world and compare the differences in the fauna and the differences in the environments, which is very, very important. Simple example. North America has a very different kind of overall paleogeography with this western interior seaway dividing the continent in the Cretaceous into two portions. Very different kind of climate, as you might expect, as opposed to Asia, Central Asia, where we have a large landmass and a lot of our Cretaceous dinosaur assemblages are landlocked, so to speak. But by using radiometric dating, we're able to confirm that we're looking at faunas that are the same age and yet in very, very different settings. So this becomes a powerful tool for looking at patterns on a global basis and looking at how our world might have been, portions of the world were evolving differently, so to speak, through time. With those kinds of important tools, it will come to as no surprise to you that we started looking at the radiometric dates in places like Dinosaur Park as soon as the Tyrrell Museum opened. These are just two unreadable front pages from two manuscripts that were published in 1990. The data that we started collecting in 1986, 87, and 88 finally made it into these two manuscripts. And the authors include myself as well as other team members from the University of Calgary and people that I'm still working with at the Berkeley Geochronology Center. The point of this is that we're still in the process of looking at the age of these rocks. We've started right back then and we're looking at it now. So right off the mark, we had a reasonably good understanding of how old Dinosaur Park was, and we've been studying that process, studying those radiometric ages, collecting more ever since. I'll take a little bit of a left-hand turn here. It's very important, though, that when you look at radiometric dates that you realize that what you're actually looking at isn't the truth with a capital T. You're actually looking at a statistical calculation. And I just wanted to get this out there in front of you right off the bat. So if we take our example, 76, just one example that we have of many, 76.06 million years, the way that these ages are typically reported to the public includes a plus or minus factor. That's called a confidence interval. In this particular example, 76.06 million years plus or minus 0.42 million years basically translates into this image where we have the age that we've calculated, 76.06, but we have some error surrounding it. And our confidence interval means that we think the age is 76.06, but it may actually fall, that age, if the data are actually analyzed over and over again, more samples are collected. There's a good chance that there's a range in which those ages are going to fall from those new analyses. And that range, based on the current data, suggests that we're going to have a range of about a total range of about 840,000 years. So yes, it looks like the rocks are 76.06 million years old, but there's an error range. And we often will report the age with this funny little symbol, Greek symbol here, theta. In this particular case, we're reporting 1 theta. This is just a statistical concept that tells us that 68% of the time our data, if we reanalyze it, are going to fall within that range. We could report 2 theta, in which case the range or the confidence interval would be larger. And in that case, 2 theta, we'd capture about 95% of the error. So these radiometric ages are statistical representations. So when you see an age like that reported, you must always be aware of the fact that, regardless of the fact that I'm giving you an age, yeah, the rocks at Dinosaur Park are 75 million years old, there's going to be error associated with that. And we have a tendency when we're talking to the public, or we're communicating quickly, is to just ignore that error. So let's talk about error. Why is there error? And I think any one of us could come up with some examples of why there's error. These are measurements, and in all measurements, it doesn't matter if you're measuring, to put new cabinets in your kitchen, there's going to be a certain amount of error in all measurements. So our measurement error or error in these numbers can be a result of incomplete understanding of the theories, the data, how the rocks are actually radioactively decaying. We may not have a completely clear idea of the decay rates. Our comparative standards that we use to calibrate our data, we may need to do a little bit more work on that. There may be some error in our understanding there. And of course, there's always methodological error lurking. Just when we put samples in a laser ablation system, The samples themselves may have some variation across the grains. The way that the equipment is working that day might have a tiny little flux in it. So there's always going to be a little bit of error, and that error is reported, as I just showed you before. The other thing to keep in mind, the reason why we keep going back to a place like Dinosaur Park and looking at those ages and trying to refine them and improve on them, is that science and technology march on over time. I mean, this is just the way science works. It's what makes science really exciting for a lot of us, because you never really ever get to the final answer and then pack up your bags and say, that's it. We can close the Tyrrell Museum and go home. We got all the answers. It just doesn't work that way. There's always improvements to be made. And those improvements in radiometric dating can involve a better understanding of the decay constants, and our better understanding of the ages of the comparative standards that we're using in the analyses. And I'll talk about the comparative standard in the type of dating that we do in a little while here. And of course, there's just beautiful ongoing improvements in our methodologies and the equipment that we use and the analytical techniques we use. So what I've done here is just thrown in a paper, the front page of a paper. It was actually published in 2008. This is the electronic version that made it into the literature in 2009. And I don't know if you can read this, but in the abstract, this is from Science, and it has important implications for the work that we're doing here. But I'll just jump in here. This calibration results in a more precise older age of 28.2 plus or minus 46,000 years, and reduces the argon 4039 method's absolute uncertainty from 2.5 to 0.25%. In addition, the calibration provides tight constraints for astronomical tuning of pre-Neogene successions, you can ignore that, resulting in a mutually consistent age of 65.95 million years for the Cretaceous-Tertiary boundary. I put this in here because it's a really cool little paper. In a nutshell, what this paper is doing is improving on our methodology, improving on our calculation techniques, and revising what we thought we knew about one of the perhaps most often repeated ages, the Cretaceous-Tertiary boundary. So it's an example of science and technology marching on. And when we see papers like that, we know that we have to take our data and revise our data and update our data. And sometimes those results, those updated results, may irritate our colleagues because we published a paper 10 or 15 years ago that they've been citing and repeating over the last 10 or 15 years, and those ages now have to be replaced. But that's life, because science is not truth with a capital T. We all know that. So, alert. I could have showed you this slide, and we all could have gone to lunch. These are the data and their distribution. It's a very confusing little picture. And what we're doing here is simply including all of these new, updated ages, the new ages that we've run, and the old ages that we've reported in a single diagram. All right? So we're going to focus on how we built this diagram and what it means and what it has to tell us and why it's important. So let's go back down to Dinosaur Park and familiarize ourselves with the park. We've got 3 formations exposed along the Red Deer River. The Oldman formation, indicated by these slightly yellowish beds at the base. The dashed lines represent the boundaries between the 3 formations. The Oldman formation is a alluvial formation. It's made up of river deposits. It's non-marine. We have the Dinosaur Park formation, which is largely non-marine, but gets some marine tongues at the top. This is the unit that we're really going to focus on. And then we have a marine unit, the Bearpaw formation, at the top. So those are the 3 rock units that are exposed. And we're extremely fortunate that we have deposits within those formations that give us datable, that have datable rocks within them, and from which we can get these types of radiometric ages. These are volcanic ash beds that are interbedded with the alluvial and river deposits. And this is just a photograph to show what one of these volcanic ashes would look like when it gets uncovered. Very, very common. The first thing that I did when I was hired on by the Tyrrell Museum and Don Brinkman took me down to Dinosaur Park and said, "This is a really cool place. You got to do some geology work down here." The very first thing I did, indicated by these little numbers, 1986, these are all the dates of the different ash beds that I found. The very first thing I did was run around the park and try to find as many datable volcanic ashes as I could find. I'll tell you a little bit in a little while why it's important that we focus on the volcanic ashes and not the other rocks. But the point here is that it's the first step. It was the first geological thing that we wanted to know. And indeed, we'd found 13 bentonites, 13 datable, potentially datable ashes in the park. Now, as we moved around the park, because the park is all three-dimensional badlands, we didn't know whether those 13 localities, whether or not we were seeing the same locality repeated in two different locations or not. So when we sat down and did a fairly complex sorting process, we found that of those 13 localities, we could arrange them into at least 7 different discrete stratigraphic horizons. So we knew that we had at least 7 different volcanic ash horizons through that section. Very, very cool, very important. And then just to jump forward to today, some many years later, can't even do the math that far, 25 years later, we've discovered that of all those volcanic ashes, really only 4 of them yield reliable volcanic ages that we've been able to work with. It's taken a lot of effort and time. And this is the distribution of those ages in a typical stratigraphic chart. So we have 1 in the top of the Oldman, we have 2 in the Dinosaur Park Formation, and 1 at the top of the Bearpaw. The numbers that you see here just indicate the name of the names here are the name of the tuff, the name of the volcanic ash, and then its stratigraphic occurrence. So why do we have these volcanic ashes in the park? Well, look at the geologic history of the area, of the region of North America. And let's go back into the late Cretaceous, and we have North America again, bisected by this interior seaway, very lush, lowland environment in southern Alberta, coastal environment. So if we get sediments coming in, they can be preserved there. They can be buried and stacked up. Very, very cool. But more importantly, we know that as we take our geological evidence from the past, and we look at what North America was doing during the late Cretaceous, so let's just take this swath from 90 million years ago to 60 million years ago. We know that North America was moving steadily toward the northwest relative to the position of the poles of the Earth at that time. So North America is essentially overriding marine crust at that time. And as a result of that, those plate tectonic movements of North America migrating, as it were, relative to the Pacific plate, migrating to the northwest, it overrides and scrapes off oceanic crust mixed with muds and waters, and those are subducted underneath the western margin, the western edge of North America. And just like a steam engine, as that melange of material gets subducted deeper and deeper, it basically, the moisture content in it becomes very highly pressurized and, in short, expresses that high pressure and heat through a succession of volcanic terrains in the western margin, resulting at that time in the types of what we call Plinian eruptions, volcanic eruptions that we would associate with Mount St. Helens. That type of explosive volcanic eruptions that generates huge plumes, massive plumes of volcanic ash consisting of glass and little crystals. So in our paleogeographic reconstructions, when we start zeroing in a little bit more, we have a beautiful lowlands landscape that can preserve sediments that are deposited on them. We have this beautiful arc terrain along the western margin of North America, which is generating volcanic plumes. And then we have dominant winds from the west that are carrying these plumes out over this landscape and letting that material deposit and be preserved, resulting in sometimes these beautifully thick volcanic ashes. And when we look at these ashes even closer up, we find that they have crystals within them. These are little fragments of rock from the cones of the volcano that blew its top at that time. And those are really what we're interested in. We're interested in those little crystals, those mineral grains. This is just a fancy little photograph of some biotite grains. These are the types of mineral grains that we're interested in. And the reason why we're interested in them is that twofold. One, those grains form, the crystals actually form at the time that the volcano is exploding. As the magma cools and gets ejected out of the volcano, the crystals are actually congealing and forming and growing. And as those crystals form, they have within them elements, atoms if you will, that are naturally radioactive. And it's those radioactive elements that we're interested in. Oh my God, the world's ugliest slide. All right, so we've got these minerals associated with the volcanoes. We've got the minerals that have within them atoms that are naturally radioactive. And what do we mean by that? Well, radioactivity simply means the spontaneous decay of the nucleus of an unstable atom. And it transforms itself through its decay into a stable atom. It goes from a parent to a daughter. This is a fact of nature. It's what drives the heat at the core of the earth. Lots and lots of evidence for this scientifically. But we only talk, it's a very important point, we only talk about radioactivity when in terms of a large population of unstable atoms. So we usually talk about an element of uranium, that is radioactive and naturally decaying into another form, maybe lead. And the particles that are emitted often change the atomic number, the subatomic particles that are emitted along with some of the protons and neutrons in the nucleus of the atom naturally change. As they naturally decay, they'll naturally change, spontaneously change the element from one type to another. And just as an example, uranium being changed into lead. So this is a natural process. There are some aspects of radioactivity that involve bombardment from gamma rays and so on and so forth, but for the most part, this is a natural process that we see. The amount of radioactive material in these rocks is very, very small. It's not enough to even be considered dangerous. There's lots of naturally radioactive materials in this room, as a matter of fact, but the amount of radioactivity is so small as to not be a problem. So, some common radioactive elements, I'm sure a lot of you are familiar with this. Carbon-14 naturally decays to nitrogen-14, uranium-235 to lead-207, potassium-40 to argon-40, so on and so forth. Very, very common. We learn about this kind of stuff in high school. A couple of other concepts we've got to grapple with, though, are decay rates and decay constants. So for every element, there is a rate of decay which characterizes that element, and it doesn't change. We can do lots and lots of experiments. We can change the heat, change the energy in the surrounding environment. It remains exactly the same. And because it remains the same, we call this a decay constant. But as you compare different elements, potassium, uranium, so on and so forth, thorium, you'll find that that decay constant is different and unique for each element, but it doesn't change for each element. That's an important point. So as the parent element decays, its amount decreases while the amount of the daughter element increases within the crystal structure. It's locked into that crystal structure. And that gives us a ratio of parent-daughter. And that decay rate is geometric rather than linear, and it's unaffected by heat or pressure. So it's a standard, doesn't change. Well, all that information gives rise to the notion of a half-life. And again, I'm sure all of you are familiar with the notion of a half-life. The amount of time for half of the atoms of a radioactive element to decay Doesn't matter how many atoms you start with, that half-life for each element will remain exactly the same in a set amount of time. Half of them will decay. So you end up with, again, typical high school textbook notion of as apparent as the element spontaneously decays, it decreases in the abundance in a set volume or area, and we see an increase in the daughter isotopes over time. And it is a geometric progression. So some half-lives. Carbon-14 has a relatively short half-life, 5,730 years. Uranium-235 and potassium-40, sort of intermediate half-lives, 704 million years to 1.3 billion years. And then we get other elements like uranium-238 and rubidium that have really long half-lives. The length of a half-life basically dictates which isotope, which element you're going to use for your radiometric dating. We can't use carbon-14 for Dinosaur Park because the half-life is too short. All the carbon-14's gone. It's already decayed. Uranium-238 and 87 for a place like Dinosaur Park with an age of about 75 million years, these half-lives are really, really quite long, and they make our calculations, they introduce more errors in our calculations because the half-lives are so long. So we tend to select the element for analysis, the radioactive element for analysis that has an intermediate half-life. I'm going to skip over that slide, just like that. All right, radiometric dating then, now we've gone through all this basic stuff, is actually a very simple technique. We really only need two measurements. We need to know what that parent-daughter ratio is in the crystal, and we need to know what the decay constant is. It's basically solving a very simple equation. We make the assumption, however, and this is key, this is the second slide that's really, really important. And this is why we can only use volcanic ashes at Dinosaur Park. We need to make the assumption that the crystal that we're studying formed and is only as old as the fossils or the rocks that we're interested in getting an age for. So it doesn't do us any good if I pick up a crystal, a mineral crystal, a biotite crystal that's been floating around in river systems and eventually landed in Dinosaur Park, but where that crystal formed billions of years earlier. Because it's going to tell me that the crystal is billions of years old, and it doesn't tell me how old the sediments are at Dinosaur Park. You need a crystal that formed at the time that the rocks and fossils that you're interested in dating were deposited. And we can get a little bit more technical about it. We don't really need to. And the point is that as crystals in volcanic magma or volcanic chambers, as they cool down, they hit what's called a blocking temperature, and that disallows the daughter product from escaping from the crystal. So volcanic deposits are really, really great because those volcanoes were blowing their tops at the time that the dinosaurs, in this particular case at Dinosaur Park, were running around. It's very important that we have the crystals forming at the time that the sediments and the fossils that we're interested in dating were being deposited. So I've just reiterated that here. These are igneous rocks, rocks generated from the cooling of magma, molten rock, that formed and cooled when the sediments and fossils were being deposited. These are the most useful for dating. And in particular, these are volcanic ashes, which we have a lot of at Dinosaur Park, and lava flows, which we don't have at Dinosaur Park, but which occur in other parts of the world. So in these cases, the parent and the daughter ratio, or the clock, the radiometric clock, starts running at the time the sediments and fossils were deposited. And as I've just reiterated about 3 or 4 times, reworked igneous rocks from older events are of little use to us. I think I've hammered that one into the ground. What do you think? Well, it amazes me how that linkage, I mean, for scientists, we often forget that we make these jumps in our understanding. We just assume that you understand why we have to use the volcanic ashes. But a lot of people don't get it. They think, well, why don't you just grab a mineral crystal anywhere? Take a river sediment and pick out beautiful little mineral crystals and get ages from them. It's because some of those mineral crystals might be really old and have just been recycled through the system. All right. The other thing we can do at a place like Dinosaur Park, I've already given away that sort of the take-home message for the talk, that we have multiple ashes. You can forget the ages on these for the time being. What we'll often do is calculate a rate of sediment accumulation based on the ages that we have. And then if we have fossils that we're interested in getting an age from that are between two ashes that we've dated, we can calculate the rate simply by calculating the difference in the age between the two tuffs. And we take an average and look at how old we think those fossil accumulations might be between the two tuffs. It's imprecise, but it's effective and gives us a really good estimate. The methods that we use, I started off using classic potassium argon, and then I moved to laser-mediated argon 4039 because it had a cooler title. Sounded more scientific. No, okay. It just is a more accurate method, and it was a method that was evolving back in the late 80s and it's become a standard method now. And the mineral crystals I use are biotites, sanidines, and plagioclases with an emphasis on the sanidines. They're the least altered. They're the ones that are really stable. And just a couple of other notes on this argon 4039 method. It's a variant of the potassium argon method. It's basically a proxy for looking at our naturally occurring potassium and argon isotope daughter parent ratios. And it's the most reliable and reproducible. This portion of this slide is the third really, really important point that I wanted to make. The argon 4039 method uses a control sample of known age. So in essence, what's used now internationally, and I could give a whole talk on how the political complexity of this mess over more than 20 years, where different labs were trying to promote different standards to use. The international standard that's used now is what's called the Fish Canyon Sanidine. This comes from a locality in the States. It's a volcanic ash that has been studied to death by numerous labs. It's been analyzed using a whole host of different techniques. And there's generally consensus now on its age. And it is really, really important because you have to include this sample of known age to calibrate what you're doing with the argon 4039. Here's the problem. Here's the essence of this talk. If you look at this list of blue bullet points, the age of that Fish Canyon Sanidine has been changing. If we go back to the 1980s and 90s, the consensus age was 2784. Fast forward to today, it's now 28.20. It keeps getting older. It's gotten older by almost 400,000 years as techniques and new scientific approaches and new calibration methods. What this means, why this drives some of you who know that I've been working on these projects for a long time and often hear me cussing when I'm working on down in the radiometric dating lab downstairs, is that it means that every time somebody down at the Berkeley Geochronology Lab or Columbia or in the UK gets consensus among all their colleagues and then changes the Fish Canyon tuff, it means we have to take all the ages that we've published on using the Fish Canyon tuff previously, and we have to recalibrate them. Now, it's not like going from 75 million years to 100 million years. I mean, we're really talking about differences of up to about 1 million years over this 20 years that these changes have been in effect. But it means, it has very, very important implications because it means that if you're trying to use these high-resolution radiometric dates to look at rates of evolution in dinosaurs and really, really calibrate the rate of evolution for organisms or rates of change in environments, all of a sudden, those ages that have been published that are sitting in the literature, you have to know all this background, you have to know what standard age was utilized, and you have to recalibrate everything. And you know as well as I do that our community, our geologic community, is international and broad, and just because somebody publishes a paper doesn't mean they will have gone back through and filtered all that information through and recalibrated everything. So all of a sudden now it's not so easy. You can't just pick up a paper published in 1993 that says, oh, the dinosaur beds down in Montana are 75.2 million years old. You have to get into those primary data, call the researcher up, find out which fish canyon standard age they were using, so on and so forth. It really becomes quite complicated and, in essence, quite political at times as well. This falls under that rubric of, science marches on. And sometimes that's a pain in the butt. A little bit about potassium-argon 4039 dating. As I said before, it's a variant of argon 4039. It's a variant of potassium-argon. And one of the things we have to do is we have to bombard it with neutrons in a nuclear reactor. So it takes time. It takes many months to send the samples out, zap them with the neutrons in a nuclear reactor, and then let the specimen cool down so the guys in the lab don't contract cancer or kill themselves due to this radioactivity. The rocks come out of the nuclear reactor quite hot, and it takes about literally 3 to 6 months for them to cool down so that they can be handled in the lab. When we're analyzing samples after they've been zapped, we want to find out what the parent and daughter ratios are, we use a laser. And the laser is extremely cool. Bring out the laser. It's very cool because it allows for very precise analyses on individual grains. So you can optically look at a single grain. You may look at the edges or the center of the grain and say, wow, that looks a little bit chemically altered there. We want to zap this portion of this tiny little crystal, this tiny little sand grain. That's what this diagram is showing you up here. You can run the laser across different portions of a single sand grain, and the results, the age results in this particular experiment, will be different depending on where you hit the single crystal. That's really cool in some ways, and it tells us that the individual variation within a single crystal can sink the boat. So we tend to be very, very cognizant and sensitive to where we're applying the laser in a single grain. And likewise, for other methods that I won't go into, the step heating method, the single grain approach, the laser single grain approach, gives us greater accuracy. This is just a picture showing what a single grain looks like after it's been zapped by the laser. I mentioned that there's error, that we have to use a standard in the argon 4039 methodology. And when we use that standard, that fish canyon tough standard, we take the data that it's generated, and the correction factor that we apply in the standard formula for determining the age of a sample is what's called the J factor. And it can get, I'm not going to walk through these calculations for you, but it can get quite complicated, and it's something that we have to pay very, very special attention to. So we use the standard, we know what the age of the standard is, and it allows us to look at the variation in all of the other isotopes that we're zapping with the laser in the grains that we're interested in, and then depending on where the standard comes in and how it's variable, we know to apply that variation to our sample. What we end up with then, after we go through all these steps, is a group of data from multiple crystals. You want to have multiple crystals from your volcanic ash, and the more the merrier. Here are 3 volcanic ashes that were analyzed by our lab here. And we end up with individual ages for each crystal with an error factor. And then we take a statistical analysis of these ages and generate a new age with an error factor. And typically the error factor is considerably less once we've taken all these data together and normalized them against that fish canyon tuff. A lot of math involved. So here's our result. And what we've done on this is we've learned over the years that the sanidine crystals, indicated by the blue squares, are the most reliable. Other crystals that we've used tend to give us pretty wanky results, some plagioclases and biotites here and here. So our range of ages, depending on the crystal we use, tends to be much broader if we include more and different kinds of crystals because there's more leakage in these crystals. So we've really focused in on the sanidine crystals, and that's what we use almost exclusively. And now I'm in the process of taking multiple samples, multiple analyses from single tufts. For example, the field station tuff. I've done an analysis on that 3 separate times. So we have an average of an average of an average for that. And that's indicated by this little star, comes in at 7703. Likewise with the plateau tuff, the first one that we analyzed at Dinosaur Park. And we're still pulling these data together for these other tufts that we have in Dinosaur Park. Pull that together for you and simplify it. What we have is our revised ages for Dinosaur Park. 77.03 at the base and going up to 75.46 in the Bearpaw. These are the new ages. These will be reported very, very shortly in a paper. And we're using this to recalibrate what we know about other localities across southern Alberta. So for example, this is an old diagram. These ages will be modified now based on the slide that you just saw. But we can take these ages and we can also now recalibrate what we thought we understood about the ages of the rocks down on the Milk River, southern Alberta, out at Devil's Coulee, many different localities that we've analyzed where we have all those data in our spreadsheets and we can recalibrate them. Very, very powerful tool. These data are also important for doing more focused work on evolutionary rates in dinosaurs. This is a diagram stolen from David Evans and Michael Ryan's paper in the Dinosaur Park book. And they came up with this idea that a lot of us were aware of, but they really codified it and have done a lot of the work on it. And this idea is that as you go through this small stratigraphic interval at Dinosaur Park, considerably less than 100 meters and closer to 60 meters, there are within the lowest 60 meters, sitting above the contact with the Oldman, 3 different faunal zones. The Centrosaurus corythosaur faunal zone, overlain by the Styracosaur lambeosaur faunal zone, and then a Pachyrhinosaur Lambeosaurus magnacrustatus faunal zone. Also, Chasmosaurus irvinensis is thrown in there as well. Well, even back in when the Dinosaur Park Symposium took place, the results at that time and the radiometric dates that we had suggested that these 3 faunal zones extended over 2 million years, 74 to 76 million years. The new ages indicate that we're really looking at something considerably quicker. That these faunal replacements and evolutionary events are occurring, in this particular case, over a span of approximately 1 million years, which actually fits in beautifully with what we're seeing in other places in the Western Interior. The Campanian, this period of time, about 77 to 75 million years, we have a very high abundance and diversity of dinosaurs. And it appears that that diversity, in part, is due to very rapid changes in both the evolutionary rates and the migration replacements that we're seeing in the Western Interior. If we were to compare that with evolutionary rates for macro dinosaurs that we see in the Horseshoe Canyon Formation, these are very, very quick compared to what we see in the Horseshoe Canyon Formation. So we're just beginning to get our hands on some very, very bizarre and interesting patterns that are confirming what a lot of us have suspected, but we had no data to work with. And that is that rates of evolution for dinosaurs seem to be, macro dinosaurs, seem to be actually decreasing in a macro evolutionary sense as we go from the Campanian and into the later part of the Maastrichtian. We don't have any idea right now what that means, why it should be so, but there's teams all over North America and Europe scrambling now to make sense of these data. And all because we're getting these higher resolution radiometric dates that allow us to probe those types of questions. And again, just to finish off, what this means is that localities that are roughly the same age in Alaska that have volcanic ashes, Montana, Utah, and down into New Mexico and even down into Mexico are now the focus of intense investigation. Try to understand if there are differences in rates of evolution as we move latitudinally, and if these rates of evolution are in lockstep with one another, but change as we go into the Maastrichtian, into the much younger rocks, 10 million years old or so, just before the KT boundary. So there's going to be some very, very important results coming out in the next, I would say, 2 to 5 years on this. And that's all I had to say about that. So thank you for your attention.